is like training robot policies, making like trying to aim for like general purpose robots. Robotics or automation, as we know, like pretty rigid in the sense that all the motions have to be pre-programmed by like very domain experts. Where like, if you have ever done some sort of robotics, you know like you would have like 2000 lines of code, and that is very rigid. And then you start adding like nuances or like edge cases on and on. And yeah, so but the dream has always been like having some GPT sort of thing for robotics as well. So basically, like you have your sensors. It can be anything depending on the task or whatever. And then you have like a perception stack. Like classically, people used to do this by having like object detectors or like having like pre-programmed like some features that they can extract from the images or the depth data, let's say. Then you have some level of task planning on top of your perception models that generally like breaks down the task into like some planning models. So let's say it's like fetching a cup of tea from somewhere. Then the navigation part of it, the manipulation part of it, is broken down into sequences. And they're like it's not linear. It's also like very complex as you like scale up to like harder and harder tasks. Take self-driving for example. Then you actually have to plan the motions of the robots, like the kinematics have to be controlled, and then there's always like a low-level controller hanging around that basically converts these motor commands to like high-frequency commands, so that the motions are at least smooth. So that's how robotics was being done, and now more and more like these parts have been replaced by like not these handcrafted solutions, but more end-to-end neural networks consuming data and having better performances. So like the perception part has been replaced by like people building like specific visual encoders, like sort of like a you can imagine like Resonate, but like on embodied data. Like those give better features. Or a lot of motion planning people in the robotic space also use like explicit object detectors. These are pretty good nowadays object detection models that give you like 6D pose of the objects and pretty accurate to use. So you can build a pipeline using this on whatever your task is. Or even like in the perception part of a robotic system, you also have to like localize your robot, and like people used to explicitly create these maps while localizing using something called SLAM. Yeah, eventually we'd like to now we have VLMs, we have like some general purpose understanding of the of like different embodied environments and some generalization shown. So like we would want the task planning stuff to also be like done with a neural net. So the why we want end-to-end systems is like clear. It's easy to scale them, and you don't get the errors that you would have in terms of like a modular pipeline. So errors would accumulate if you have like 4 or 5 systems working in sequence, but the having like a giant neural net to consume all the data and do the same thing is like more scalable. In terms of this, there are also like multiple things you can think of. So up till now, you have like your sensor data coming in, and you have to generate like robot like a task plan of the instruction. Let's say it's cook like make tea for me. Like it has to comprise of multiple instructions, and like you can think like a good way to scale this can be thought of differently in terms of like text or like code functions, or even like having goal images. So like let's make a tea. You can have like semantic instructions of like pick that up, put some cubes, boil the water and everything. But that's not grounded enough for like the embodied environment. So you can have like images as well. Like let's say instead of having goal instructions at every step of your task, you can have like goal images that you can train the subsequent models on, like this part on. So yeah, so people have tried this, and all of this is like since 2022, after like GPT sort of blew up. So and like people tried scaling up like vision language models as well. So yeah, they're somewhat good at like generalizing across domains and making these plans. But you can think like, okay, there's an obvious flaw of like the loop closure here. Like these plans at least have to be grounded to the robot as well as the environment itself. So like if the robot says go bring the tea, and then second step is that, but like the first step cannot be executed, or like it does not make sense for the robot embodiment. Let's say it's a wheeled robot and that has like one arm. So all these things are there, and people are tackling them by like having a modular approach. Like people coming from systems background, okay, let's just have like some code functions to call in the low level, and then give that as prompt to the VLMs and try to fine tune on that data. Something like that is being tried, at least. Yeah, so these are the ways. And then as we go on further, like what the end bit is, like you would want everything to be consumed by a large neural network. You just collect demonstrations of humans doing stuff, or even like humans operating the robots, and then use those huge trajectories to like make a generative model out of it for actions. But currently people are doing two things, and it's not. I mean, the problem itself is hard, but scaling the whole thing also doesn't make sense. So, for example, if I collect data on like decluttering this table, then it's a very long horizon. So, like, why this doesn't work at all, and why people are doing this right now I mean, as I said, like, if you just give like the first VLM planner that I'm talking about, generally people just use it off the shelf or like try to improve VLMs for embodied problems. Like Llama on like embodied data would be this VLM planner, and it can do the task, like break down the task into like just sequences of action, tasks, sequences of subtasks. So that's the part. And what is VLA? VLA, so people refer to like these models as like vision language action models, or large behavior model, LBM, or like essentially what they're doing is just behavior cloning or imitation learning on real robot data. That's it. And yeah, so this part I think like you guys like, because you guys also have been using VLMs for different applications, you know, like just to steer them into the right direction is hard. So this part, I guess, for large corporations that are training VLMs will crack. But the other part is something the second part, like where you can imagine you have broken down the task into like subtasks, and then you want to have a neural network that takes in like your observation history and the robot joints, because that is important. That's also part of your state, and has you're breaking down task into like sub goals. Like these sub goals are generally like, it's easier to scale them in language. So like collecting a whole bunch of data of folding shirts, putting cup in bin, opening drawers, opening shelves, everything in language can be a goal. So it's just easy to scale in language, like Android language instructions. So yeah, so this is the part like a lot of companies are now putting in money to scale up. So yeah, I'll talk about like first the data and like the design of these architects and how they're different from like how you would imagine just training like a large transformer on text, now videos, okay, now action. So seems okay, fine, everything should work. But yeah, we're not there yet, and there are like good reasons for it. First, talking a bit about data. So this is OpenX. This is like 2023. It was like a 1.5 year effort between like 50, 60 institutions across the world, and everybody just compiled all the data that everybody had been gathering for like years and years and never shared, but they just compiled it and open sourced it and made it into this format. So it's like usable by everybody, like this common format. So yeah, this was the first effort, and then people from this Google Robotics team started a company and then now they've collected, first it was 4K hours of robot trajectory, now they've collected like 10K hours. This is also a graph I found from like 1X, from the 1X team. 1X that makes like those humanoids, neo robot humanoids, if you've seen them. So they, in the talk they were saying like they are going to like just double the whole amount in like a month. So like they have that many fleet of robots and teleoperators operating. But you can imagine so this is what they collected, the physical intelligence company collected in like a year, like 10K hours of data. So if you see, so this is a recent talk at Coral by Kevin Black, like one of the guys who was training these models at Pi. So like he compared like the OpenX data that I showed, 4K hours, Pi, GPT-2 and then Llama 3. So this is like a crude comparison because I mean it's just hard to compare token to token because so he just did it in like number of hours. If you have like average reading speed and then this many tokens per word, then the scale is like we're obviously not quite there yet, like not even close to like what we had with GPT-2. So just don't expect any GPT-2 movement. There are other options as well, like other sources of data. Just like pure is like Pi is collecting like pure robot data, like on the robot, which they think is like the purest. But there's also simulation that's little less useful in terms of physics, but you can scale it up like 100,000x if you have more compute. Yeah, we have a data scarcity, but how much data is like actually necessary? So like you guys might have seen a lot of good demos for like collecting data and then training robotic policies. But this is like one of the recent papers that the Google team did, where they like made the task very hard. So like here it's just one task, just start collecting data again and again. So for easy tasks, success rates are pretty good. For like the harder tasks, like actually folding a shirt and making it harder, or like tying a lace, even though the human teleoperators all have like collected 5,000, 8,000 sort of demonstrations, which means like almost like hundreds of hours of teleoperation data. The performance does not scale. So like this is also a question right now, and people say different things for why this is happening, why it's not scaling with more data. It can be that the set of disturbances is actually quite huge, but this is like a huge effort with the whole Google Robotics team. So like if they could have easily, they would have possibly collected more, but this was maybe too taxing on them. So yeah, the scaling laws are not good enough yet, and it can be that the set is quite big, or we need like better mechanisms explicitly to like counter disturbances or recover from. So yeah, I mean these tasks are they specifically chose like dynamic tasks which involve some sort of motion. So like tying a lace, it's not so by dynamic or quasi-static. I mean like quasi-static, you can imagine a task where like you at any time stop you can stop and like nothing will change in the environment. Okay, dynamic is like you have to do it with some motion. So like hanging a shirt is one, right? You can imagine tying a shoelace is also. So like in these dynamic or very contact-rich tasks, they like showed like okay, scaling is probably not helping much after like even going from 100 to 8,000, 7,000 demonstrations. Like not much improved. Yeah, and this is like all the data only on this. There's no multitask policy. Yeah, so after data, like I want to talk about like design, like how do you actually train these policies. And so all of the policies that are trained are basically or like being scaled up are basically derived from like diffusion policies paper that came in last year, or this ACT that also came like last year in the starting. Yeah, I just quickly go through the details. There are some subtle differences that you guys might notice if you have experience with diffusion models. Okay, why robotics people want to try diffusion? That's quite obvious. Why? But there's also a good property in like diffusion models in particular. So robotics data inherently is like very multimodal. So like picking up a cup has like 1,000 different variations. So like you can collect 1,000 demonstration and all of them will achieve the same result, but they are very there's no right one answer basically. And in order to capture this multimodality in the data set, you need expressive architectures or solutions. So so this is where like energy-based models come in. So like in your classical neural network, if you guys know, you just have a feed forward, you predict, and then there's a loss, right, between your prediction and the output. But in an energy-based model, you're not predicting your output. You're actually predicting a function of your input and the actual output. So you're training this. So yeah, so energy-based models have, so after you have trained like your neural network to model this energy function, now what you want to do is like you do argmin over your output. But energy-based models is, you can think instead of actually doing the prediction, you leave the prediction to inference. So like you just model a function of your input and your output, and then do an argument over that function to actually get the output. This is like just a manual process, right? This is done at inference, but this is the function that you train, the neural network that you train. And it's like, it's like if you think about why, like these are like very just analogous pictures of the same thing, because anyways you have to predict why. But you can quickly notice like there's a relationship between these. Like if your energy function is like this, then you can express the probabilities by this by this integrating over y hat, like your prediction basically. You have explicit policies. After that, you have some action representation, like mixture of Gaussians or categorical representation that you sample from. So the multimodal part is not really captured by the policy. It's just done on top of the policy. But if you have energy functions, the policy is capturing that, and you're just doing an argument. And yeah, and diffusion models are also energy-based models with like a small twist that instead of modeling the energy function, you are modeling the gradient of the energy functions. It seems to be like more like better just in every other case. So yeah, that's why diffusion. And I guess I don't know. So for people not familiar, if how you training or like how you formulate a diffusion process is like you have some data, and so okay, so this is your data, sorry, and then you start with like a normal distribution, and then if you start denoising it, or like you can think of like the other way around. If you have like an image, just keep add noise to it, and then after k steps, you just get like a Gaussian noise. That's it. So what you're trying to learn here is this noise prediction network. So at every time step, if there are like k steps of this denoising process from going to an image to like the actual data point, then you are trying to learn this noise prediction network, and that's the mapping you want to learn with your neural network basically. So that's at every case. So you have to do like apply your neural network forward pass k times to actually get to like the actual data point. And yeah, then that's just a regression on your loss, your data point with your noise prediction network. So this is like the standard diffusion model formulation, and it's similar in like how we do it for policies as well. So there's some nuances. Okay, so here what you want to like denoise is like the action sequence. So you want to go. This picture is I think helpful. So you want to go from like an action sequence of like let's say 10 time steps to look from this to like something like this. Like if you keep adding, so this is your data that you collected, and then you keep adding noise to it to like get like basically nothing, this noisy actions. And what you're trying to learn is, as I said, like this function, this noise prediction function, and what it's here right now is it takes in your observations, and which are like the observations I mean by the image, robot image, as well as the robot state pose. That's your observation. It also takes in the noisy actions, and for k time steps or like k forward passes, you're trying to like denoise those actions. The difference here is like this is your, just so you can imagine y actions. You can also imagine, okay, you have like a robot trajectory, observation, action, and you can just try to denoise the whole thing, right? Just start with noise and try to denoise observation and actions as a whole. But practically speaking, this is like this like increases the inference time a lot because observations are very high dimensional. So what people generally do is like instead of actually denoising the whole observation action trajectory, just denoise the action trajectory and condition it on the observation. Yeah, if you see like just LSTM doing behavior cloning or BET, just a transformer, just a simple transformer. Like people have observed that diffusion models are better for multimodal data. Like that's a fact. And okay, how much of this multimodal data is distributed in video or language? We can make an argument about that. I don't think we have like exact measure of which data is more multimodal, but diffusion models capture multimodality better. There's another reason maybe why this works well. So this is like okay, multimodality. I've been saying multimodality all along, but like this is like a small experiment you can do. just collect like a data set like this, okay, and try to train like a neural network to actually imitate it. You will face mode collapse in like any model you train, except for like some energy-based models that are better at capturing this data. The denoising is like conditioned on observations, not actually just denoising action and observation. The reason for that is inference. Like if you have to like generate images also along with the actions, that becomes like a harder problem also, and yeah, very slow like at generating real-time actions at like 5-10 hertz. Yeah, so this is something else. These are some design decisions which I don't know if you want to get into. Uh, yeah, so this paper basically like why it's famous is because they showed like very good like robust performances in like all these robotic tasks. So they had like whole 4 or 5 pages only for like experiments, which is like non-typical for like a robotics paper. Generally, they just want to do something in some small set of experiments, but because their results were so good, they did a lot of experiments. So yeah, so the task like this, like pushing some T to like desired goal position, uh, just done like in like 130 demos, something like this, of like flipping a mug and placing it, also done in like around the same. So like this also like spreading the tomato on the pizza. So they did like very impressive numbers in terms of number of demonstrations collected. So that's why like it's sort of the standard. So this was how like people started like really believing in like scaling up robotic data, because now with 50-100 demonstrations you can have like pretty good policies for tasks that you could not program before. Like doing a motion planning solution for like lifting a cup from arbitrary positions is like super hard. So it's a good signal to scale these up. And yeah, people have scaled these up, as I said, like all the data sets collected. Another thing that they have been doing while scaling this up is like, okay, we are training or scaling these up from scratch, but because anyways we have like the observations coming here, like the observations and the robot goal, which is, as I said, mostly in language. This is language and vision. So like, why don't we like make use of the backbone also of like VLMs? So like we can get some representations that are good for embodied data. So like some good pre-training or initialization for these policies. So yeah, they also tried that. So this is like the similar architecture I showed you in diffusion policies, just a different form, but essentially same thing. You have an encoder, and then you have like you have an encoder of the image and the language goals. And how you do it is different, like different architectural choices. But like you have an encoder that encodes image and the observation goals, also the robot state, and then the output or the latent space you get after the encoder, that is fed into like a decoder, which is actually doing denoising. Like as I said, denoising actions conditioned on these observations. So this is doing the same thing. This is a different architecture. And what they did was, okay, we are doing this. Let's just replace the encoder with like already pre-trained vision language model, and like the image encoders of like your robot images with like something like Siglip. So these pre-training representations that you get from the VLM can actually boost performance or like boost training. So they tried this, and it was better, obviously, but and they made some architectural choices why. Yeah, so directly just doing this also does not make sense in the robotics data. So there are like nuances why this is better or worse compared to like this which they came up with now. So one of the reasons is like this. So have you guys heard of like cross-former? Maybe in vision. No, there's like a recent meta paper. So the point that they're trying to make is like, instead of conditioning on this, you should have like a more auto-regressive pipeline, and that's what they did later on. So why this and why not this is like, the reason is, okay, if you have like a pre-trained VLM and people start with like a pre-trained VLM and then do subsequent tasks. If you have a pre-trained VLM, actually the representations of the last layer do not contain meaningful things. So it's generally that the more meaningful representations are captured in the previous layers or somewhere in the middle, but the last layers are actually just for predicting the like more focused on like the vocabulary or predicting the vocabulary correctly. So if you just pass this on as the condition, then there's like it's not maybe that helpful. But instead, if you like pass the whole thing as like a
So giving more information.
yeah. So this is something like that. You can
Makes
imagine.
sense.
Just have better use of these representations. This is how like the pi zero model is right now. Yeah, that's what they did in the pi zero model, and the results were like sort of at least the results in terms of what they did with the demos were pretty good. Like they observed a lot of like stabilizing behavior in like very hard tasks. Like they also had like a whole 10-minute sort of video of like full laundry, autonomous laundry, just picking up, doing and then reshelving everything. So it was pretty cool. But in terms of like the numbers of why they're doing all this, like their hypothesis is like, okay, we're going to scale up robot data, but we're going to scale up in like a multitask and multi-robot embodiment format. So like different tasks, a lot of different tasks, but also a lot of different robot embodiments. So yeah, their whole bet was like, okay, we will go for diversity in terms of robots, in terms of tasks, and like try to create some foundational model or like a model that people can pre-train on their like use the model and then fine tune on their task. So like it gives them a boost. So this should be their like initial, what do you call it, like initial results, at least in scaling of multitask and multi-robot data. You can see like pi zero or like the same model trained on scratch on one task, from scratch on one task, versus their model, which is like using first a pre-training approach on all the tasks and then fine-tuning on the new task. The gap is like relatively smaller in like most of the tasks. Sometimes it's not even there. This is diffusion policy. This is ACT, OpenVLA. So these are all like just different model classes. But yeah, so you can see like the gap is not that high in most of them. Sometimes it's worse. So this is fine-tuning data in number of hours they collected. Sometimes it's worse, sometimes it's good. But yeah, maybe some early signs of like positive transfer, but not quite there yet. And yeah, more. So instead of like just betting on multitask, multi-robot embodiment data to have like a backbone for all robots, a more practical approach that companies are taking, like 1X are taking. This is also from like Eric Zhang's talk. So they are doing everything like in a closed loop on the current robot. So they don't believe in like multi-robot embodiment data, just because they have money, I think. So like he was saying like, okay, somebody asked him, okay, what's going to happen when you have a new robot? What are you going to do with it? He said like, we don't care. We'll have enough funding to like collect the same amount of data in like a month or two. So we just don't want to go through the effort of like mapping that data, making sense of it.